Okay, I'd like to welcome everyone to the Mile High Video Conference Talk Workshop. It's up in Denver, and I'd like to thank our sponsors over here, the Dash Industry Forum, the Streaming Video Alliance, Wave, and the Ultra HD Forum. And also, I'd like to thank Lorraine Hagendorf and Jennifer Privitali for arranging for the logistics on this. And here's the ground rules. So everyone, I know you can't get name tags yet, but register with Jennifer and pick up your name tags later. We have breakfast, coffee, we'll have lunch in boxed lunches, and then there'll be a reception tonight. So that's what those tickets Jennifer is handing out are, drink tickets. The thing is, it's a full and packed agenda, so we'll be keeping a strict time, or I'll be keeping a strict time and a cane for people on the speakers. So the speakers need to start on time, and then I'll let them know about 5 minutes before their time is ended, so if they can take questions. And then after the workshop, please complete a short survey, and this will allow you access to some of the slides and recordings for those speakers who have given permission. So once you finish the survey, we'll give you a link and password for that. For any questions, ask the people up in front. You can ask me. Ali is here in a purple shirt down over there. Dan is right next to Ali, and Alex is someplace around here. Okay, and that's about it. With our first speaker is Dan Grois.
Hello. I'm very happy to welcome all of you here in Denver. Thank you very much for coming and attending our workshop. I would like to express special thanks to Ali, Alex, and Yasser for great organization, and hope you will all enjoy the workshop. So let's start. I'm sorry for people who are standing there, because we really need to start. We have a quite tight schedule, and we need to continue, so you will be able to see the presentation later, recorded. Okay, my name is Dan Grois, and I'm giving a tutorial on the video coding and HEVC. How many of you attended this workshop last year? Can you please raise your hand? Okay, so it's not too many. Actually, last year I was giving a tutorial also about video coding HEVC, include HDR, and for HEVC part, I just allocated something like 20 minutes. So now we have more time, we have 1 hour. And normally, if you would like to provide a detailed explanation about HEVC and all extensions of HEVC, or at least some of the extension, you need much more time. So normally it takes something like 3-4 hours, and this is what I did in the past in different conferences with my former colleagues in ICIP, ICME, ICCE. Today we have just 1 hour, so please be focused. I will do my best to emphasize the most important aspect of HEVC and make also introduction to video coding. How many of you actually work with HEVC? Can you please raise your hand? Okay, great. Not too many, but it's fine. Okay. So let's start. My tutorial actually will have 4 main parts. It's the first part. I will provide a brief introduction to the block-based hybrid coding, followed by a brief description of HEVC. Then I will discuss HEVC version 1 and also partially version 2. I hope you will have enough time because we started a little late. And finally, I will provide future insights for video coding development. And of course, later we will have Gary Sullivan also talking about the VVC development. And what I will provide here, what I will talk about regarding the future development is what was happening before April this year when we started to work on the VVC standard. Okay, so let's make an introduction to the block-based hybrid video coding. What is the video compression goal? Somebody can tell me. I want also to participate, that you will participate and make some inputs. What? Yeah, exactly. We would like to efficiently condense visual data while minimizing the loss of visual quality, right? And what actually, why we need to compress the video? To reduce the storage space, right? To reduce the transmission delivery bit rate. Okay, so it's correlated here. Okay, so we have a sender, normally some kind of HD video with a high bit rate, like 600 megabits per second. We would like to efficiently compress the video, okay? And we would like to reduce the bit rate to like 1% only. We can do it today with HEVC. Less efficiently, we did it with HEVC. And finally, we get at the receiver video content, which can be decoded and efficiently presented on the video display. So without the video compression, of course, we couldn't do all that. What is hybrid video coding? Okay, hybrid video coding actually relates to division into blocks, okay? And then performing some kind of prediction, such as intra or inter prediction, followed by transform coding. So I suppose most of you are familiar with this general approach. So if you have a current picture, we have a previous picture, we would like to find the best match in the previous picture, right? To get the lowest residue here, right? And then to apply some kind of transform. Normally, things are more complicated. For example, the best match can be found not just in the previous picture, it can be found in another previous picture. Yes, so we again find the best match and then apply some kind of a transform, such as DCT transform, discrete cosine transform, which is the most popular transform. Okay, we actually convert the spatial domain pixels into transform domain coefficients. And after that, we normally apply quantization, such as scalar quantization, for reducing a number of levels for transforming coefficients. What are actually the goals of all this process is to adjust bit rate versus fidelity and remove subjectively irrelevant details, right? Now, we have two main standardization organizations which are actually handling all the standardization process. One organization is VCEG, Video Coding Experts Group, formally structured as question 6. Okay, originated in 1998. And another group is MPEG. It's called the Moving Picture Expert Group. It's established in 1988. So this year we actually celebrated 30 years of establishment, and those who attended standardization meetings got quite nice jackets, so it's worth attend standardization meetings sometimes to get some present once per several decades. Okay, but it was very nice. And now we will briefly review the HEVC, just as a reminder, as introduction to HEVC. So most of you probably remember that the first model was introduced in August 1999. The joint video team was formed in 2001. And then finally, HEVC was approved in May 2003, followed by approval of the extension, such as fidelity rate extension, and later also multi-view extension and scalable video coding, scalable extension. Now, common HEVC profiles are presented here. You're also quite familiar with them. So you have a quite popular main profile, high profile, baseline profile. And this structure is actually called, I have a pointer here. It's not, okay, laser point. Okay, so this structure is called onion-like structure. Because if you can, as you can see, baseline profile is mostly inside other profiles. Not fully, but mostly. Also, if you take a look at the main profile, it's fully incorporated within the high profile, etc. So it's onion-like structure. Now, if we look at HEVC as in general, we can say that HEVC is actually based on hybrid video coding, yeah? And it's quite similar to other standards, however, providing some new things, some new tools, such as enhanced motion compensation, transform coding with smaller blocks, improve the blocking filter. We have entropy coding, which was enhanced. And if we compare the compression gain to its predecessor, MPEG-2, we get something up to 50%, more or less, okay? Which is quite nice. So this is the basic coding structure of HEVC. Also, I suppose you're all familiar with the structure. Of course, we have here macro blocks, division on 16 Luma blocks, plus 2 chroma blocks. Normally, the input is provided in 420 subsampling. Okay, we have also quite other common features with previous standards, block transform, we have variable block size motion. So it's fully, not fully, but it's mostly based on what we had before with quite significant improvements. Now, let's take a look at the macro block level. So for prediction purposes, we can further split the macro block to smaller sizes. We have different types of units. So we have 16 on 8, 8 on 16, 8 on 8, etc. Okay? And the motion accuracy is with quarter or 8-tap filter. Now, H.264 also introduced multiple reference frames, okay, which was quite nice. And by such a way, we can provide a better prediction. We can jointly exploit scene cuts, aliasing, uncover background, and other actually quite nice aspects. Also, it introduced weighted prediction. We can actually select from multiple reference pictures and assign particular weight. For intra-prediction, we have directional spatial modes. We have overall 9 types of different direction, as you can see here. I think my pointer is not working. No, it's not working. We have 9 different directions. For the transform coding, we have a smaller size transform. Okay, in addition, we have a repeated transform of DC coefficients. Okay, so it also provides some kind of additional gain. And for entropy coding, we have a context adaptive variable length coding. Okay, which actually allows us to execute coding of all symbols except for transform coefficients. And we have, of course, a context-based adaptive binary arithmetic coding, ABAC, which was proven to be very efficient. Now, this is more or less in general just a reminder for you for HEVC, and now we'll start with HEVC. Okay, so HEVC, generally it's more complex than HEVC, as it expected. And now we will provide, like we will review the main aspect of HEVC. We don't have time for getting into more detail, like in details into each tools, but at least we will, it works, okay. Which one? Oh, okay, excellent. Okay. Now, by the way, I'm working on the book on video HEVC, on high-efficiency video coding, which we will publish next year. It will be fully printed in color, published by Cambridge University Press, so you are invited to follow this. Now, let's talk about the history of video coding standards. Do you know this guy? Somebody knows who it is? Okay, I see some people know. And this is actually William Stanley Jevon, and he actually said the following, and it's called Jevon paradox. The efficiency with which a source is used tends to increase rather than decrease the rate of consumption of that source. And this is what we also see in video coding field, yeah? Some times ago, people were saying the video coding is dead, like we already have HEVC, yeah? The compression gain is quite nice, so why we need another codec? Why we need to compress it more like, why we need the better gain? So it's not the case. We do need better gain, and currently we are also working on the new video coding standard, which is called HEVC, and I suppose it will continue and continue. And my dream, like really, I want one day to come into my room, have displays all over my room, and just press a button, and be in a different place, like appear on the beach or in the forest, etc. So I suppose in 10 or 20 years from now, we can be able to put displays instead of walls. And of course, for that, we need efficient video compression. Yeah, what we have now is not enough for that. Okay, so I will cite the Cisco report. I suppose you're already very familiar with this report, and many people cite it, but as you probably know, it's expected that IP video traffic will be around 82% of all consumer internet traffic by 2021, which is just 3 years from now, which is very, very impressive. And of course, today we have, I always say that different types of content which we didn't see some years ago, such as dog TV, we had the cat TV, and we have many different other channels. Yeah, by the way, what do you think, like the dog TV? What dogs likes to see, like how it looks like? Somebody have some ideas?
Yes, subtitles.
Yeah, it's right. Okay. So normally dogs likes to see dogs. Okay, I have a dog, by the way. I don't have a cat, so I also suppose the cats like to see cats. I never see a cat watching TV, but I think some cats do it. Okay. So think about that like 20 years ago. It's like, it was not be possible. So yeah, it's all because of HEVC.
But HEVC is not efficient for the dog eye model.
Yeah, really? Okay, I didn't know that. Okay, I will check that. I didn't know that. Okay, so for enabling actually high quality video services, we need efficient video compression techniques, especially for 4K and 8K resolution, and also for 16K, etc., what we will have in the future. Now, application. Of course, the application range is very wide. We have internet streaming, we have real-time conversational services, broadcast, etc., etc., etc. Really, the range is very wide. We also have medical imaging. The work on HEVC started in 2010. Actually, at that time, ITU and MPEG established a joint collaborative team on video coding, which is called TVC. And call for proposals was issued, followed by extensive development of about 2.5 years. And finally, HEVC version 1 was approved in 2013. Version 2 was approved in 2014, including also range extensions, scalable extensions, multi-view extensions. Later, in 2015, HEVC version 3 was approved, including 3D video coding extensions, which calls 3D HEVC. Then, we have also version 4 in 2016, which included screen contents coding extensions. And finally, this year, we also had the HEVC version 5, which include additional CI messages that include directional video messages, monochrome 10 profile, main 10 still picture profile. Okay, so this is more or less the history of all versions of HEVC that we had. Of course, the most important is version 1, which was approved in 2013. Now, what is important to emphasize is that the scope of video coding standardization mostly relates to decoding process itself and related syntax, okay? So this actually permits optimization beyond the obvious, yeah? We can allow complexity reduction for implementation, and of course, we do not provide any guarantee on quality, okay? So this is actually more or less the scope of a standard. For HEVC, we had something like 27 complete proposals. Each proposal had a major packet, a lot of coded video, experiment. We also conducted a lot of subjective testings, really a lot of testings. And the quality was compared to its predecessor, HEVC. Now, not so surprisingly, most of the, like all proposals, more or less were based on H.264 HEVC. They also like included hybrid video coding structure, okay? It's also included block-based motion compensation, spatial interprediction, and all these known tools. People do not tend to, like, we do not expect really to change the approach, yeah? So this is also what happens with the HEVC, and this is what, a little less, but what is happening with VVC, with the new standard. Gary will explain it later. But with HEVC, it was quite obvious, more like it was really based on what we had before. It started here in 2010, ended here 2013. High-level design of HEVC similar to that of AVC. We have a network abstraction layer, NAL, okay, and we have a video coding layer based on hybrid video coding, as we can see here. And now we'll get a little more details. So, coding layer design. One of the unique features of HEVC is actually allowing to code based on so-called quadtree structure, okay? Starting from a grid of so-called coding tree units, or CTUs. Here you can see a grid of these CTUs, so-called coding tree blocks, yeah? They have fixed size for Luma and Chroma. And normally, Luma CTB size is typically 64 on 64, but can be also set to low sizes, such as 32 on 32 or 16 on 16. And they are processed in raster scan order. Actually, coding tree block is a root of the coding quadtree. You can see it here, yeah? And it's, as you can see, it's actually traversed in so-called Z-scan order. In the next slide, you will understand the more details. So we have a coding quad-tree structure like that, and this allows actually, we provide actually larger, it's very useful for larger block structure, especially for HD and UHD resolutions. Okay. Because we have like larger resolutions, the structure was proven to be working really good. So each coding block can be split once into prediction block, OPB, and recursively it can be split in so-called transform blocks by using the residual quad-tree, so-called RQT. Okay? So once we split it, for example, in 2 prediction blocks, and then we split it in additional transform blocks. So you can see here depths of 3. So we split it once, second time, and also third time. And this is the reason why the depth is defined as 3. And overall, if you look here, we have 10 transform blocks. Okay? So once we split it into prediction blocks, and then we recursively split it into transform blocks. This slide actually presented very nice. So you have a Luma coding blocks, and you have a Luma transform blocks here. Okay? This is in blue, and this is in red. This structure was proven to be working really well, and we have really nice gain because of this structure, and this was one of the main tools of HEVC. Okay? This is what provided most of the gain for HEVC and made it so popular. We have different prediction block partition modes. We have partition modes only for interprediction, including asymmetric motion partitioning. Okay? And RQT size, the trees that we discussed before, RQT, like the transform sizes are ranging from 4 and 4 on 32 on 32 in the same way that we have seen before. And all this actually allows adaptation to varying space frequency characteristics of the signal. Okay, so these actually trees perform really well. We now see some results. If we compare using of different CTU sizes up to 64, we get a very nice gain up to 25%, which is really impressive. Okay? So the larger CTU sizes we use, normally the larger gain we get. Here we see a comparison results of using different TU sizes. Again, if we use TU sizes up to maximum of 32 and 32, we get a really nice gain of something like 17.5%, and it's also very impressive. The same with the PU sizes. Okay, if we actually allow all modes, okay, we get the gain of something like about 30%. So it's really impressive. Like this, again, this structure provided most of the gain for HEVC. Now, about the interprediction improvements. Interprediction of HEVC had quite many drawbacks. It provided inefficient range of supported coding block sizes. Number of direction was limited, just 9 direction. It was insufficient prediction of homogeneous regions, and also inconsistency across different block sizes. So all that was resolved in HEVC by performing the following steps. The reference samples were computed with 132 PL accuracy. We added additional directional modes. So now we have 33 directional modes, which is quite impressive. We provided reference sample smoothing, boundary smoothing, and all prediction modes actually unified across all block sizes. And here you can see different direction which are provided within HEVC. Okay, you see here 33 different directions. In addition, we have a planar prediction and DC prediction. For chroma, we just have 5 modes, such as planar, DC, horizontal, vertical. Horizontal, just a second. Horizontal, this is this one. See here, and this is vertical. Just a second. Okay. Now, regarding the reference sample smoothing. So in HEVC, the sample smoothing is performed in an adaptive way based on block sizes, directionality, amount of detected discontinuity, and it has 2 smoothing modes, normal filtering and strong filtering. On this actually diagram, you see how we apply the smoothing. So the green dots are represent a reference sample smoothing, and the yellow dots represent samples which are not smoothed. Okay, so it's first of all based on the block size. It's based on the direction, on the angle itself, And it's based also on discontinuity by comparing minimal distance of direction to horizontal and vertical mode. Okay, so this is a really nice implementation here. Now, about the boundary sample smoothing. So, as you know, by applying interprediction modes, some discontinuities can be introduced along block boundaries. So we actually apply boundary sample smoothing for TB sizes less than 32 and 32. We apply it on a horizontal prediction mode, vertical prediction mode, as well as DC interprediction mode. And we do not perform in HEVC boundary smoothing for chroma TBs in order to reduce the computational complexity. What I would like to say is that during the whole standardization of HEVC, the complexity was one of the quite important issues, as well as parallelization. Like many tools have been proposed and developed in order to parallelize as much as possible different aspects of the codec itself, okay? Such as, we will talk about a little later, such as the blocking filter, also some entropy coding aspects, okay? So parallelization and complexity was really considered and all these aspects were taken into account during the development. About the interprediction. So for interprediction, we actually allow to improve motion compensation by asymmetric motion partitions, by providing so-called reference picture sets, okay? And more efficient data coding actually included so-called advanced motion vector prediction, merge mode, block merging. It's a very nice tool that we actually introduced into HEVC. And we also provided motion data storage reduction. It is not applied on 4-on-4 blocks, and only unit prediction for this area, for this sizes, was used to reduce the memory bandwidth. Again, as I said, memory bandwidth, complexity, and parallelization was quite considered during the whole development process. About the transform quantization, prediction residual is transformed, its predecessor HEVC and other standards. We have the core transform of 4 to 32 and 32. These are integer approximation of DCT. What is important to notice that actually matrices of the smaller side transform are subsampled versions of the 32 transform matrix, as you can see here. Okay, so this is actually a larger matrix of 16 on 16, and if you would like to make it smaller, you just subsample it. Okay, so the smaller matrices are subsampled version of the big one. And also what is important to notice that the transform is separable two-dimensional transform. It's also made to reduce the overall complexity of the transform process. Some additional quite unique transform which was introduced to HEVC is DST transform, discrete sign transform. It was applied only to 4-on-4 intra-residual. The reason for using this transform is because of how the interprediction is performed. It's known that prediction error during the interprediction increases with a larger distance from the boundary, okay? And DST vectors, DST basic vectors are actually better fitting such a behavior. So in HEVC, we use DST for intra-residual of 4-on-4 prediction blocks, and the reduction is something like 1%. Okay, it's not too much, and this is the reason why it was only restricted to 4-on-4 Luma transform blocks, because it provided marginal benefits for other transform cases. About the quantization, so quantization is quite similar to that of HEVC. We have a CU level adaptation. The coding of QP performed differentially within the CTU. And we have also frequency-weighted quantization for providing quantization matrices, okay? So actually for larger transforms, such as 16 on 16 and 32 on 32, we provided subsampled quantization matrices of site 8 on 8, okay? And by such a way, because the matrix is lower, we actually use the same quantization step sizes for groups on 2 on 2 and 4 on 4 adjustment coefficients. But it's also like possible, and we also use it in HEVC. Now, about the in-loop filters. So for in-loop filters, we actually have two basic filters. One is the blocking filter, another one is a sample adaptive offset filter, SAO. Why we need them? Okay, so we would like to remove the coding artifacts and preserve edges, okay? The blocking filter is similar to what we have in HEVC, but it has a reduced number of filtering strengths and also better parallelization, as we discussed. We have another filter which called sample adaptive offset. It has two main different offset methods. One, in individual mapping of with H offset values. Another method is relates to nonlinear amplitude mapping function with band offset values. I will discuss them in more details now. So, regarding the deblocking filter, when we actually design the deblocking filter, we would like to carefully consider the following aspect. Okay? First of all, that the filter has a direct impact on the subjective picture quality, right? And second, we would like to understand if the block boundaries that we would like to filter is a natural age or maybe artifact. So, yeah, what is a natural age? For example, text. In text, we have ages, so it's okay. We don't want to filter them. And this is the reason why it's make it a little more complicated. And also, we would like to understand which filtering strategy to apply, like how strong to filter the boundary itself. Now, in HEVC, the deblocking is performed on 4 sample portions of 8-on-8 block boundary. When we actually held the following conditions, one condition that the block boundary is a prediction unit or transform unit boundary, and second, that the block boundary strength is greater than 0. Okay, this is 2 main conditions. Yeah, okay, we also have another one, but it's like the variation of the signal on both sides of the block boundary is below also a specific threshold. So we have a mathematical equations according to which we decide it. Now, first of all, we split the picture on 8-on-8 regions. Here you see dotted areas. These areas represent non-overlapping blocks of 8-on-8. And these non-overlapping blocks can be deblocked in a parallel manner, okay? And this is provide better parallelization. This is what I was speaking about. So we have here horizontal edges, we have vertical edges, and we have these non-overlapping blocks of 8-on-8 samples. And the strengths vary from 1 to 2. We have just strong filtering, weak filtering, or no filtering at all. And by following this condition, it's actually decided which strengths to apply. The strong filtering is applied on 3 samples on both sides of the block boundary within the 4 sample segment, as we've seen before, and it's similar to HEVC. And we have also weak filtering, which is applied on 2 samples on both sides of the block boundary within the 4 sample segment. Okay, so that's what we have for the deblocking. Now, about the parallelization. So, as we discussed, it has improved parallelization. We can actually apply filtering on vertical block H in parallel with the blocking of any other vertical block H. It's very nice, right? Also the same with the horizontal block H filtering. We can, any horizontal block H can be deblocking parallel with any other horizontal block H, okay? And actually the updated sample values after a deblocking of the vertical block boundaries are used as input for the horizontal block boundaries. So it's quite parallelized and it's really good. Okay, so parallelization was, as I said, very important aspect of all HEVC design. Now, about a couple of words about SIO. So it's actually designed to add corrective offset values by attenuating systematic errors, which are introduced by phase shift, and also attenuating the ringing artifacts, or so-called Gibbs phenomenon, which is introduced mainly by large transform sizes. So we have 2 main methods. One is nonlinear amplitude mapping function, and another one is individual mapping with H offset values. We don't have time to go into details. Some of you who are interested, we can discuss this later, how it works in more details. And an additional important part is the entropy coding part. So we have here entropy coding. In HEVC, compared to HEVC, we just have one entropy coding scheme called context-based adaptive binary arithmetic coding, or CABAC. It was proven to be very efficient, and this is the reason why we use HEVC only this scheme. Okay? It's used adaptive probability models for most symbols. It exploits symbol correlation by using context. Have also a restriction on binary arithmetic coding based on the table lookups and shifts only. And compared to HEVC, it's provide reduced number of contexts. We wanted to reduce the complexity and to make the process faster. And it's provide a reduced number of context-coded binary decisions. And also remove dependencies. So these are main improvement over HEVC. And also, I would like to note, yeah, this truncated write codes. This is a new feature, new codes that have been added to existing scheme, truncated write codes. Now, about the coding of transform coefficients. So subblocks and the 16 coefficients in the subblocks are processed by using so-called reverse diagonal scan. It works like that, okay? You can see here, okay? It's called reverse diagonal scan. In addition, we have also horizontal scan, and we have a vertical scan based on intramodes. So, oops, sorry. So we have here the intramodes, the vertical modes, horizontal modes. So based on the intramodes, we decide which scan to apply. We have also several alternative coding modes, several alternative coding modes, so-called spatial coding modes, special coding tools. One is transform bypass, another one is lossless bypass, and the intra-PCM mode. So what are all these modes? The transform bypass actually signals NTB level, and it's useful for graphic content. For example, if you have such sharp edges or flat areas, okay? Particularly when we have a screen content coding applications, okay? And in such a mode, Kabak context of transform coding are directly applied to prediction error signal. This is transform bypass. An additional bypass is so-called bypass or lossless coding. It signals NCU level and actually bypass scaling, transform, and in-loop filters. So we will see now some diagram showing this bypass. Okay? And the last one is the intra-PCM mode. It leads to direct coding of sample values. Normally, this mode is applied in some urgency situation in cases when we actually the encoded stream produce more bits than the uncoded samples. It can happen when we have a lot of noise and some kind of uncorrelated data. It's not happen too often, but it can happen, and this is the mode for such an emergency situations. So on this diagram, you can see different these different bypass modes. So here is the intra-PCM mode. We actually bypass all the process. We have a transformer skip mode, and we have here a lossless mode, okay? So-called lossless mode, or transform quantization bypass mode, okay? So this are also quite nice special modes, which can be used in some particular cases when encoding text, graphics, or some particular content. Some words about the high-level syntax. So in general, what is high-level syntax? All syntax elements above the slice segment are called high-level syntax. They actually relate to access to packets, settings of low-level coding tools, random access information, metadata, etc. We have several parameter sets. We have a sequence parameter sets. We have a picture parameter set, similar to what we have had in HEVC. And in addition, HEVC, we have new parameter set which called video parameter set, or VPS. It describes overall characteristics of coded video sequences, including the dependencies between different layers, and actually enables comparable extensibility in terms of signaling. Okay? So this is one of the new features which was introduced. It contains, for example, maximum number of layers in the bitstream. Also contains some information about maximum number of temporal sublayers. It contains information about profiles, tires, DPP parameters, layer set, etc. Also contains some data about HDR parameters as an option. For version 2, which includes Rext extension and scalable emotive extension, it also contains information regarding the scalable modes, okay, etc. And in addition, we have a so-called SEI, or Supplement Enhancement Information, and VUI, okay? They are quite similar to H.264. Some examples of SEI messages, buffering information, picture timing, frame packing, okay? Display orientation, and for video usability information, some examples. We have a hypothetical reference decoder information, clock parameters, color space, etc. Parallel picture processing, parallelization tools. As I said, as we already discussed many times, these tools are very important. We have some tools. First of all, we have a slice coding. Slices can be coded independently, as you can see here. We split the picture into slices, okay? And we have dependent and independent slices. The dependent slices actually inherit previous entropy coding state, okay? For slices in loop filters can be disabled, okay, at the boundaries, okay? So it's also one of the options. And it's by such a way we can perform some kind of parallelization. An additional tool is tiles, which are actually independent rectangular regions of the picture. As you can see here, the processing of the tiles is in raster scan order, and CTU-wise in raster scan order within each tile itself. As you can see the numbering here, it starts from 0 here and goes like that, okay? And the last tool is the wavefront processing tool. This allows actually to run several processing threads in parallel in a slice over rows of CTUs. And we have also some delay that allows this adaptation, as you can see here with the arrows. So it starts actually processing this row and then another one with a small delay. And the Kabak contexts are inherited from the row above. So if we compare these tools and also look at the performance of the tiles, here is the performance of the tiles, you see that if we have just one column and 70 rows, because we have actually defined the tiles in different shapes, we get the largest losses. So when using the tiles for different purposes, such as region of interest coding, yeah, you should carefully decide before what will be the number of tiles that you would like to use, because in such cases it really leads to a very high loss. And this table summarizes the performance of parallelization approaches. So if you take a look at the wavefront, you have actually the lowest coding loss compared to tiles and to slices. It also doesn't have boundary artifacts and single core issues, but it cannot be used for region of interest coding. So for region of interest coding, we can efficiently use tiles and should define the number of tiles in a proper manner. If we take a look at the profiles and levels and tiers of HEVC, we have a main still picture profile, and we have a main profile, main 10. It's an onion-like structure, okay, as we actually discussed before. And let's take a look at the gains. Okay, I would like also to provide some comparisons to existing coding solutions. So of course, blue line here is HEVC. It provides very nice gain compared to AVC. And here you see some numbers related to HEVC main still picture profile. So for main still picture profile compared to AVC, we had a gain of something like 17% and gain of about 44% compared to JPEG compression, which is considered to be quite old. And this is another. This is another representation of average bitrate savings relative to JPEG. Okay, so you can see here that HEVC provides 44% relative to JPEG, and AVC provides only 33% gain relative to JPEG. About the subjective verification test that had been conducted, we can clearly see that the gain even larger. So if we can say that based on objective test, we have a gain of up to 50%, it's normally like around 40%. Yes, based on the subjective verification test, the gain is much larger. So for UHD videos, we have a gain of something like 64%, which is very impressive. When developing HEVC, the main focus was on high resolution sequences such as 4K, and we really achieved this goal. So 64% is a really big achievement. Okay? And for lower resolution, we have somehow lower gains, but still above 50%. Now, I would like to introduce some results which I also did with my colleagues. We also have some comparison of different contexts later today, but I would like to just say a couple of words. In 2013, I presented a paper comparing HEVC to VP9, and we have proven quite nice gain of 43%. Here you can see some curves showing this gain. We'll be able to take a look at the presentation later, because I suppose from the last rows it's very difficult to see the lines here. This work was also presented a little later in the SPAE 2014. We have a comparison of low delay configurations. For low delay, the gains are a little lower. Okay, so for random access, we have a gain of close to 40% compared to X264, which was at that time quite well optimized. you know. It was 5 years ago, and related to VP9, we have a gain of 43%. The minus actually shows the gain because it's in terms of BR rates. This paper was presented at SPIE last year. The result have been generated by me and with my colleagues. And here we have a more recent comparison results. So compared to HM is the reference software of HEVC, compared to VP9, we had a gain of 46%. GEM, by the way, I will speak about it a little later, but it was a reference software for future video coding exploration. So compared to GEM, we actually had an overhead. Okay, it's expected because it relates to future video coding tools. Yeah, and related to AV1, HM performed by 30% better, and all this for rate control enabled applications. Okay. Just a second. Here I have some typo. It's for rate control disabled application, not enabled. It's for fixed QP test. Okay, when actually we disable rate control, and by such a way we provide better comparisons of particular technical tools. And for this one, it's for rate control enabled. So for rate control enabled application, we have a little lower gain because HM doesn't have rate control. So the rate control is enabled in V1 and VP9. Now, we have even more recent comparison results, which have been performed by my former colleagues, presented in PCS 2018. So this is based on quite recent versions of codecs. If we take a look at HM, it performs better by 21% compared to AV1, which is a version of February this year, and better than 40% compared to VP9. And this is for rate control disabled scenario, when we disable rate control, okay, to not allow the optimization of the rate control have some influence on the codec performance. This is the right thing, the right way to test the codec. Because if you do allow rate control, you actually allow to introduce some differences, like some rate control optimized issues into the comparison of technical tools. And this is not the right thing to do. It should be disabled. About the encoder runtimes, HM actually performs quite fast. If we compare it with AV1, it performs like 30 times faster than AV1. And GEM, compared to HM, performed much slower because it was the reference software for the new feature video coding, which is not optimized. But surprisingly, it was still performing something like 4 times faster than AV1 codec. Okay, these are results for when the rate control enabled. So here we have a better results for VP9 and AV1 because they have rate control, and HM, GEM actually don't have such a rate control. It's not the main aspect. And these are the coding times. So the coding times are a little slower. Okay, so you can see GEM compared to AV1 performs such as like 2.5 times faster, and HM performs something like 20 times faster compared to AV1, which is also quite impressive. So HEVC was proven to be very good from all technical aspects, and really like people invested a lot of efforts for developing this codec. So it's a really good one, and we should use it. Now, I would like to say a couple of words about HEVC version 2. In HEVC version 2, we have so-called format range extensions. We have a multi-layer extensions, which includes scalability extension and multi-view extensions. Okay, we use them a little less. They're not so popular, let's say so. Okay, what is important to emphasize that these extensions have been developed more or less from the beginning, like have been considered more precisely from the beginning of the HEVC development, compared to MVC and SVC extensions of AVC. Yeah, and the reason was like we wanted to make this extension really used by industry. Okay, the industry uses extensions, but not as, I think, in my opinion, not as intensive as it's planned. But anyways, these are really nice extensions, and I will explain a little about them now. So for the next extension, we would like to extend 420 810 bits consumer-oriented scope by high-quality distribution, right? We would like to have this one. Contribution in broadcast, we would like to use some kind of medical images applications. We would like to efficiently compress high-quality pictures, etc. We have actually three main categories. One is our necessary modification required for HEVC version 1. Second category relates to coding efficiency improvement, and third one relates to precision and throughput optimization. Okay, so these are main three categories which have been considered during the development of REXT extensions. And as a result, we got 21 profiles in addition to what we had in version 1. It's very impressive, okay? It's really a lot of profiles. Like if you look at the table, we have many different options, so take whatever you need, okay? In green, you see here the profiles which have been used for version 1. So you have a main steel profile, main profile, and main 10 profile. In addition, you have a lot of different profiles. Now, about the SHVC, scalable approach. So the traditional approach is to encode and store a separate video stream for all possible clients and connection speeds, right? So this is what we normally do. And scalable video coding says the following: encode a common base layer and then add an enhancement layer as needed. Okay, so this is like the whole, the overall motivation, overall approach of scalable video coding. So if we have different clients varying by resolution, frame rate, quality, etc., we actually have a base layer and we have a quality enhancement layers. So we have different type of scalability, and by such a way, we allow each device to decode whatever it needs. Yeah, the most important is to get something decoded, you know, and not get black screen or some kind of black regions on the screen. Okay, so we would like at least base layer to be decoded by all devices. So this is the overall approach of scalable video coding. As we discussed, we also had scalable video coding for HEVC, which unfortunately, in my opinion, did not become so popular as it was expected at that time. Now, in general advantages, we have less storage space, we have less data rate in multi-broadcast environments, we have more flexibility, we have built-in support, and of course, error resilience, where unequal errors protection, which we can apply for base layer and enhancement layer. So we should protect base layer better, because it's like if the decoder doesn't get the base layer, it cannot decode the whole stream at all. Okay? And it also has some disadvantages. We have an overall overhead, and we have, of course, a little higher, depends on the application, but higher, a little higher decoder complexity. Now, if we take a look at the SVC, which is a scalable extension of HEVC, we have a single loop approach. Okay, so we parse the base layer, we parse the enhancement layer using the information from the base layer by decoding the base layer intra-blocks, and then we decode the enhancement layer, and overall we have just one decoding process. And as an opposite, in a scalable extension of HEVC, so-called SHVC, we must actually decode the base layer, upsample results as reference signal, and then they decode the enhancement layer, so we have a one decoding process per layer. Okay, so this is the main difference between the scalable extension of HEVC and scalable extension of SHVC. Now, if we compare the advantages, for SVC, we have a low decoding complexity. We always require changes in low-level coding tools. And as an opposite, in SHVC, we have a high decoding complexity, but we allow to reuse of existing single-layer designs as base for each layer decoder. So this was one of the main aspects when deciding to use this multi-loop decoder approach. Okay? Now, the type of scalability that we got. We have a temporal scalability, higher frame rates, enhancement layer, for example, 30 frames for base layer and 60 frames for enhancement layer. Spatial scalability, of course. We have we allow higher spatial resolutions in enhancement layer, such as, for example, 720p resolution base layer and 1080p enhancement layer. We have a higher SNR quality, so-called coarse grain SNR scalability. For example, we have a 1 megabit low quality base layer and 8 megabits per second for high quality enhancement layer. We have external base layer scalability, so we can use as a base layer HEVC. It's also very beneficial. We have a bit depth scalability. For example, the base layer can be coded with 8 bits and the enhancement layer with 10 bits. We have interlaced to progressive scalability, color gamut scalability as well, such that we can actually provide BT709 color gamut in the base layer, followed by BT2020 in enhancement layer. So these are different scalability types, and it's quite nice to have all of them. Now, a couple of words about MV HEVC, which is a multi-view extension of HEVC. Use cases. Of course, we have to view 3D movies, different programs, multiple view display, sorry. And the changes that have been introduced in this multi-view extension of HEVC were based actually on high-level syntax only. So multi-view extension of HEVC is quite similar to multi-view extension of AVC. And it allows also, what is important, to reuse the existing HEVC encoder and decoder components. Okay, so this was the main decision why designing the multi-view like that. Okay, we wanted to reuse also in scalable extension and also in multi-view extension. So this was really important. And what about HEVC in general? So the outlook for HEVC use in digital video market is extremely positive. It was provided by quite recent research. Okay, the curve here is rising, so we expect growth in the deployment. And yeah, it's a good standard. Also from the technical perspective, so yeah. And the question now, what is next? What is the next beyond HEVC? Now, as some of you probably know, the standardization activity of new video coding started already in 2015, which is 3 years from now, 3 years ago. That time, the joint exploration team, video exploration team, was established by organization MPEG and VCEC. And they started to work on so-called JEM, Joint Video Exploration Model software, okay, until April this year. And in April this year, we already started standardization of VVC, on new video coding standard. Couple of words of tool which actually provided some improvement of coding efficiency over HEVC. So it was proposed to use larger block sizes, okay, more than 64 and 64. It was proposed to use larger transform sizes beyond 32 and 32. 5 minutes. Yeah, I know. It's okay. I have a timer here. Thanks. We also tested, like it was proposed to use additional transform in adaptive manner, yeah, in addition to DST2, to DST7 and DCT2, okay. Also, it was proposed to have much more directions. You can see here, many directions. So we have just 33, now 65. And all these tools provided an additional gain. It was proposed and incorporated in this GEM, okay. And if you take a look at the timeline, so the draft for call for evidence was issued in 2017, and actually then we issued the call for proposals, and the call for proposal results have been provided in April this year in San Diego standardization meetings. And at these particular meetings, we already started to work on new video coding, which is called VVC, okay? So as I said about this new video coding standard, Gary Sullivan will make a talk later today. So what is next? The next is VVC development, which already started in April this year. So this is more or less what I wanted to say today. We actually provided an overlook over HEVC compared to its predecessor AVC, and also provided some insights about the new video coding, future video coding development. And I hope you enjoy my talk and questions. Thank you.
For anyone who has a question, I have a mic over here. I can't see anything because there's so much light.
It's a little light here, so it's...
I'm asking about the scalability versus the current approach of adaptive streaming. which is to ingest multiple different bit stream for every bit rate and every resolution and so on. So is there any joint work with Dash or something like this to adopt this scalable into the adaptive streaming?
I think yes. I think like this question you should maybe ask tomorrow when Ali will give his talk. It's like, as I know, yes, the answer is yes, but it's not so like, it's not so popular as expected. You should ask this talk tomorrow for Ali, okay? Because he is more work with Dash and all these streaming solutions.
Okay, you mentioned that the biggest gain come from the bigger block size,
Larger block sizes.
Larger block size.
Yeah.
But in the later slide, you say even for 480p, the gain was like more than 50%. While the like
480p again. Which slide do you remember?
So you have a later slide. You say for 4K it's actually 60-something% of gain, but for 480p that's 50-something%. So I wonder that if the gain mainly from a bigger blocker size, so why the smaller resolution also can harvest the coding efficiency gain?
No, but the block sizes, again, the block sizes you decide, you start from some particular block size for each resolution. Like you have 1080p, you have smaller resolutions, but if you have like flat areas, for example, blue sky, yeah? So you should not divide on smaller blocks. If you divide on the larger blocks, even if you have low resolution, 480p, right? You can shoot the sky, blue sky with a smaller resolution video, right? So if you divide the blue skies on the large blocks, you may encode them in a more efficient manner, okay? Because you need to send less information to the decoder. So it doesn't matter, like you also for the lower resolution, you have again, smaller gain. Why smaller? Because the overall picture size is lower, okay? So you have less blocks, yeah.
So thank you, Dan. We are going to take a break until 10:10.